Is it okay?
Okay.
And the goal of the framework was to improve the low accuracy of traditional load assessment systems. That was our opportunity. And in a nutshell, traditional loss assessment comprises of two phases: pre-earthquake phase to prepare the system and to activate the system in the core earthquake phase. And first we have to create a portfolio, building types, and to define damage states, and to establish a ground motion model, and now to form relationships between them, damage prediction between ground motion and damage states, and to quantify loss. And usually it is done by ratio and replacement values. So basically in the core earthquake phase we are waiting for the earthquake to get the input, and then using the predetermined formulas we turn that into currents. This is all fine, but each step contains a lot of uncertainty. In generating shape maps, both in algorithms and in measurement of ground motions, it's approximation really. Then in fragility curves, if we are talking of analytical models, then we tend to approximate actual buildings with theoretical types and theoretical buildings, which is largely not true. And in the empirical approach, we use only a limited data set, because one earthquake is one set of data, and maybe try to import from other earthquakes, but it's so again approximation. And then we make approximations in loss assessment, in replacement value and in ratios, because we say 20% of replacement value for moderate damage state. That is also approximation. So if we approach to loss assessment in an analytical way, we are actually multiplying all of these uncertainties which happen in each step. And if we use the empirical way, if we use locally gathered data, it's the picture below, we have only one fraction of the earthquake, and then we imagine the rest of the curve. And we try to overcome this by using other earthquakes for same building types, and we say it's transferable, but again, not really. In terms of accuracy, scientifically, it's all very well and justified. And the reality check when we try to estimate loss in currency is that according to Hazes, it's a factor of 2. It's not 20%, it's a factor of 2. So we can say that traditional loss assessment is rapid because it's minutes, but it's not accurate, even though it's perfectly scientifically justified. So we tried to do something else. Instead of using only earthquake engineering knowledge and creating the model before the earthquake and making assumptions and introducing uncertainty, we try to introduce machine learning and construction management, but not by itself, informed from earthquake engineering, and to create the model after the earthquake. That's the biggest difference. And then we would have real buildings and real damage. This study relates just to houses, since the Kraljevo earthquake was not very strong, and that was the data we had. But nevertheless, the framework could work with other buildings too. How does it work? So first, machine learning learns the mapping between the building characteristics, building types, and the associated damage state, after observing damage state on a sample. So when an earthquake happens, we observe real damage on real buildings on a sample. And besides that, we try to improve the logistics and made a cost matrix. We try to move away from replacement values and ratios and investigated the methods and the quantities and the unit prices to repair a certain building type from a certain damage state. So all the combinations were approached differently, because it's one thing to repair cosmetically damaged state 1, that's painting mainly, and the other thing is to repair damaged state 3, which includes new columns and reinforced work and everything. So we investigated different building types and different damage state one by one. And also we introduced, we call it the soft rule. So when calculating costs in the end, we use the probability of a building belonging to a damaged state. And not the hard rule. The soft rule, and the error from the hard rule was around about 20%, and it was reduced to 5% just applying the soft rule. So it's generally an improvement in any system, because at the end any system must calculate all buildings, all repairs to get to the whole currency value. So this is basically the system. And now we tried a couple of things. First, we investigated if machine learning can learn the damages and the building types. And we had a sample of about 2,000 buildings. Got good results, but not good enough, because here we have some low recall and precision measures. But it was due to the fact that we didn't have enough buildings in all columns and rows. Not many buildings, for example, in damaged state 4, because it was 5.4 earthquake, and that is what it is. So we have we can conclude that we can use it, but not in this way. We have to choose those buildings differently. And we got that promising result that the soft rule works very well. Even though this confusion matrix would be better, we got an error only 5%. Let me remind you, Haas's factor 2. And there is a reason for that, because when we make mistakes, they are both under and over the diagonal, so they cancel each other. And even though we make mistakes in particular damaged states, we get a good result in overall currency. What we did next, we tried different representations of a building, which is the input to the machine learning. First one is earthquake data and location data and building data. And we tried different combinations and got almost the same results. So we concluded that we actually don't need earthquake data to predict earthquake damage. Same results if we don't use Acker-Bommer or whatever. And that's why we chose to use these representations. Geocoordinates, building type, year of construction, number of floors, and footprint area. It's not because we don't like earthquakes, but because this is easy to obtain anywhere. It's basic geometry of the building, but it is actually earthquake engineering informed, because these parameters also capture the seismic behavior, the height, the type. So it makes sense, but we tried, we got the almost same results. And now this is actually a machine learning problem, and buildings are seismometers for the damage that was caused. And it doesn't have to be an earthquake, it can be a meteor. Because we now look at the damage across a territory. And this is now the crucial element of the framework. That is representative sampling, because in real life we can't have many buildings. We have an earthquake and we can see some of them immediately after the earthquake, and we have to choose well, so we have all building types and all the damage states in the matrix. And how do we do it? We apply the K-means clustering algorithm, because you see here we have some different houses there. The combination that we are looking for is building type and number of floors, because it's good representation of seismic behavior. And then this algorithm chooses this group, and this group. out of all types, all combinations, and then chooses one representative building from each of these smaller classes, or 2 or 3. But now we have all examples, so machine learning can work. There are no empty columns, like in that first example which I showed you. And that enables for the framework to work with a small data set, and that in turn enables speed, because not many houses are needed. So we devised a framework. In the pre-earthquake phase, unlike traditional approach, we form a database of building. Every system needs that. Then we form a sample that represents the portfolio well in advance. So if we have 1,000 houses, we now choose in advance 200 houses, which would be inspected the moment the earthquake strikes. And we make sure in advance that it is a representative set, that it is a good representation of the whole portfolio. Then in advance we train a group of assessors, we turn to people, maybe cameras. In the future we turn to people, because there are people everywhere, to detect damage on that sample. So for example, 10 people are in that group, and they know, they have a list of addresses in their neighborhood, and they go to check, is it DC3 or DC4 or DC2? And then they upload that to the computer somehow. And of course there has to be a cost matrix prepared before the earthquake. When the earthquake happens, those people go and detect damage on the representative set. Then the random forest machine learning model predicts damage states of the rest of the portfolio, and using the matrix we get the cost. And we do that every day. And now if this process was 2 months, this wouldn't be rapid. But with each cycle, the accuracy improves, and since observing the representative set takes a couple of days, so it's not minutes like traditional loss assessment, but it's days, it's not weeks. The prediction process can be categorized as rapid. On the example of Kraljevo and the 2010 earthquake, there are 40,000 buildings there, 6,000 were damaged. And now we are looking at the representative set of 10%. So it is 4,000 buildings. It's about 57 assessors, 30 buildings, 35 a day. It's 2 days. So it's rapid. Why 57? Because they have hail protection there. People who go out and do stuff when it's thunderstorm. And for example, those kind of people, or maybe some that are better educated for construction, can be trained in advance and have a set of buildings in their neighborhood to detect damage. So that's how it works. And this is the last slide. What is the accuracy we got? For a 10% representative set, we got the relative error of 14%. And this slide shows that for the same size, there is a 70% chance that it is that the relative error is under 20%. So comparing to traditional, it's much, much more accurate. And it's different because in traditional, everything is done before, and we apply the formulas. And we do the opposite. We prepare in advance the cost matrix, the people, and the representative set, and then send people to observe real damage on real buildings. And it's a really unique and different system, which was derived from this multidisciplinary approach, because actually we don't know much about earthquakes, but when we saw the accuracy problems, we approached it differently and got very good results. And if you give me just one more minute, because I was listening carefully this morning, the work done behind this cost matrix really is a link with Nikola, with Vesna, Because the first information regarding resilience is how much it costs. And you would get a very good number for 2 days. Maybe even Helen, this you use replacement values, ratios. Maybe there could be another layer of predicting repair costs. And replacement value in cities is one thing, in rural areas is something else. It is less than repair cost. And especially Vesna, because behind these are methods, and she starts with the network. We have the network behind these figures. And also Nicola, because he's very good to overcome bottlenecks. But what is driving the process? Financing. And now we know what the government gives, how much, and what is needed to not make it another obstacle. And the procedure, the number of engineers, you also mentioned that example, the procedure and the cash flow. And the government could get it in a couple of days. So just because these workshops are about sharing knowledge and communicating, I wanted to finish with that. Thank you.
Excellent presentation. We definitely need your expertise. So you're invited to our next workshop. We don't know when it's going to happen, but I think it's in 3 years. Yeah, exactly the date. Thank you very much, Zoran. Any questions for Zoran? This methodology and has been well published in several papers. And Nicola has paper.
Yeah, I have a quick comment. So I think it's a great idea to use building seismometers, as you mentioned. And but for me, when we talk about crowding, it's a specific case where your strategy worked. So what would be interesting is to see how it works in other earthquakes.
Oh yes, we would love to have that priceless database to try our methods.
Because it's priceless.
We know, but we don't have money anyway, so
because
we can't wait really. Because it is one case, one set of building types, and it was specific.
Soil classification also. So because here
yes.
your buildings were, I think, a good indication of the losses because the soil was pretty uniform. So you could exclude these things that were pretty uniform distributed around the region.
Yes.
But if we look at Dures, for example, where you have really soft soil and then a different kind of soil, then I'm not sure your buildings are going to be enough.
No, but the point is that geo-coordinates contain the information
yes.
about the soil. That's the
So
main
you include the soil then?
No, it is included.
The soil is not included,
Nicola,
but it's inside the XY coordinate.
It was for us it was a surprise. Because when you put geo-coordinates, they are somewhere, and that is a particular type of soil. And when we exclude soil and leave the geo-coordinates, we get the same results, because that information is included in the location.
So that's the point. XY coordinate contains a lot of back information about
yes.
the...
Also, the footprint area, number of floors, height, and the building type, it captures seismic behavior. So we don't need a PGA.
Yeah.
I'm trying to take the job.
Nice. Nice try. Very interesting presentation. It's got me thinking. I was thinking originally 4,000 buildings you mentioned, when there were 6,000 damaged, that's a lot of people to send out. But then I was remembering work that Eve is doing and work that's being done in ETH on putting sensors in buildings and maybe using that to very quickly assess it. So already putting sensors inside those 1,000.
Yes, but sensors detect PGA. We need to detect
no,
damage.
So they're working on using the sensors at different heights of the buildings and getting the actual
Yes,
response.
cameras also. Another way to approach this is have aerial images or drones or something, but you also need people to look at the pictures.
Yes.
And we chose for this framework the simplest possible way, because earthquakes happen, unfortunately, in not so rich countries, and maybe they don't have the infrastructures with those. Yes, but they have people.
Yeah. The only thing is those people might should potentially be going to the buildings that are red tagged to get people back into the buildings, rather than maybe going looking at buildings. that aren't
Absolutely.
damaged. So
This algorithm,
resources,
that is the first information to go to see if it's DC4 or one of those lighter. And another feature of this algorithm, it learns from the first day. When they get good results from somewhere, they don't send them there. They send them when they get mixed results. For the second day, it's not automatic, but I didn't have time to explain everything. That's another good feature. And probably in Zagreb, which is a city, we would have to modify something in this algorithm that chooses buildings, because they're all Zagreb, you know, this is all spread out individual houses. So I'm not saying this is now perfect for every, but for cities like Kraljevo, they can implement to have this framework now. They just have to make the portfolio.
They just need to pay.
They have to pay for the database, because it took us a year to get 2,000 houses, whole year.
This is what we got.
And Josip is giving it in 5 minutes.
I need to comment on the PGA. I think it's excellent that we don't need PGA. I think everyone in this room understands and acknowledges that PGA is not the best damage predictor of the right on the structures. And I think soon is going to be already it is abandoning.
I'm sorry,
design code. But I would like to say that it's a good thing that you're going without the hazard or the ground shaking, right? But from your expertise, right, what you showed here, 2 days, it seems rather a long time.
we can discuss
Is
it.
it enough? Is it this time constraint something that of course has to be reduced, because rapid loss assessment is basically very rapid, and we are looking in Switzerland of hours to react.
Yes, but Boža was telling me about different earthquakes, and he told me that it was weeks, months before ground surveys were done enough in that area to get, so for those earthquakes 2 days is
I think
very rapid.
Josip can say, or Markel, how long it took in Albania and Zagreb or Petrinja to give the estimate about the damage state of all.
And we can tell the government after 2 days it's 1.5 million.
This is different focus.
And that is
Yeah,
very
every state is one
important
thing,
for
and
them.
usability is another thing. If you
Okay,
allow
also
the-
usability.
the-
How long it
this
took-
is completely
how long it
rapid.
took
The information
give
from
the
rapid
usability
information
of the house?
usability. It's
And I must say something else. This is the step about rapid loss assessment, and we don't need PGA, but we need PGA for everything else. Machine learning, no, machine learning is not transferable. The traditional loss assessment is transferable because it's building types with calculations and formulas. We can just do this one earthquake when it happens. It's different approach. We are not saying we don't need PGA. When Boža was talking this morning, it was 10 different topics. One of them is rapid loss assessment, where we possibly don't need.
It's a very interesting concept.
Josip, maybe.
Mark, I will answer your question. 1 month, majority of the buildings, 80% of the buildings, 1 month. In 3 months, every building, but it's crucial for Solidarity Fund is 15 weeks for application for Solidarity Fund. That was we are chasing on the field to get a lot of data to make assumption of.
You can't avoid ground surveys with engineers to fill out a big form because it's about monetary transactions. This is a quick evaluation only about the damage state, because we can't exclude ground surveys. But we could include, which is now not in the surveys, some kind of indicator of quantity. That is something for global systems and procedures. Because then we could switch to method, quantities, unit prices, and be more accurate. Because in ground service forms, there is no information about the quantity. Because you can have tiny cracks, but millions of them. And it is this C1. And maybe you have just one crack for DC3 and this is more expensive because a lot of paint job needs to be done. We don't have quantity in those surveys.
I think this one has some sort of extent, it's 2/3 of the building.
That's needed. That's needed. Qualitative, a lot, not so much.
To answer to Marco and to say something about that, it has been 1 to 2 months, around 70,000, 17,000 building inspected, but a lot of discrepancy are there because of this kind of knowledge that you need. And coming to machine learning, even that is a problem. We are talking about an event that can happen each 10 or 20 years. So it would be a problem how to use the previous data, or we need a larger region in order to use the data from one place to the other one. Because if you are talking to the same place, maybe it will be somehow difficult, because after 20 years, this machine learning is not going to...
Machine learning is not prepared one time and then used 10 years later. It is algorithm, when it happens, it will act, and we have to update the cost matrix and the building portfolio. But machine learning will start to work when it gets uploaded the first day. It's not transferable in time nor place, nor space. Sorry.
On the data training, did you see improvements with size, right? With the number of buildings?
Yes.
What if such data sets are coming together? Of course, the building typology is a problem, but at the country level, where you have the same.
In the whole Balkans, the building types are the same. We would like to try different things. I can't for sure, maybe Milos is my colleague for IT and machine learning, but I can't be sure to tell you if it's possible, not possible, better, not better. The transferable, maybe it's different kind now of simulation. We could maybe simulate damage and then see what happens, and go back to the vulnerability curves to see what kind of earthquake. You know, it's a different steps. If we wanted to make it transferable, we can't do it without PGA and vulnerability curves.
But you need a larger
to make it even transferable. We now admit it's not, but maybe it could be. We would like to try. This is Milos Kovačević, part of our team and responsible for representative something, K-means and machine learning.
I think that from a machine learning point of view, that this system is completely independent of building types, completely independent of PGA, because you only evaluate after the earthquake. You go to the place where earthquake happens, you see what is going on, you have geo-coordinates and you have basic building characteristics, and then you're able to build that kind of model. Your building types could be green, red, blue, never mind, but you must ensure that this labeling will be uniform across that area. So this is not a predictive model in advance. This is the model that just is capable of estimating the damage caused by that certain event which occurred in that place, and geo-coordinates plus building characteristics uniformly labeled contain all information. So I'm really surprised that nobody did that in estimating after the earthquake. But when you want to predict what will happen, when you want to regulate construction, etc., you need a PGA, because you don't have in advance a prediction, but that way. But when you just estimate what happened, what is the induced damage, then this is, from my point of view, from my experience in other types of machine learning, ground irregularities, almost anything that is related to that local area. But you must, there is one big if, you must select good representative sample.
And who is doing that? Who is selecting good representative samples?
In our algorithm, we did it automatically by using, but you can intervene in expert knowledge. There is no problem with that. But here we divide the whole set of buildings, the whole building inventory. We divide it into subcategories according to building type, number of floors combination. So we have one subset of buildings for each building type, number of floors combination. And then we have, in each subset, we have coordinates.
That is
And
roughly 24 groups.
And let's say that we have one subset with one floor BT1 type. All buildings in one city that are BT type 1 and one floor only. And then we have a spatial distribution of that kind of buildings. And now we apply k-means clustering algorithm in space in order to represent the points around which buildings tend to form clusters. And each point, each center of the cluster is one representative building. And now you can use even more than one in order to, when the earthquake happens, you will see if in one cluster, if you have more samples, if you have a big entropy about different damage states, in that case, you can go and pick more houses from that cluster. In other clusters in which you have all damage states uniform, you don't need to go there. So you can adapt in base, and it's not also limited with days. It's limited with people that are going to. With number of people. If you have 2,000 people, then it will be maybe hours. Yes. But the quality of
you don't need quality. Probably you can do crowdsourcing because everyone has a phone, and you can have 40,000 buildings.
Good idea.
But
yes, but the problem is with quality of assessment.
No,
But like booking, if you solve it like booking.
the problem is not the quality, but the sophistication. So you cannot use, let's say, people self-assessing the status of their house.
Yeah, because they want more money from government.
You cannot, of course, you're legally not allowed to do that, and the quality will be quite low because everyone will pretend their house is almost collapsing, although it's only minor cracks. But you can use such approach to pre-select where to go, because if your assessment criteria for self-assessment of the owners are robust and simple enough, they won't make too many mistakes. So in the first hours you can have this, then the estimators will be focused on some areas. They can also, and it will be another thing that you said that like 35 units per day for an estimator. This is, in my opinion, very hard. But if the estimator can need only to do the damage, and they already have from the owner area, floors, structural systems, and most importantly, this is a bit tricky, interventions, because the people know what they did. Most of the information will be already collected and already available.
Those are specified buildings. That street number 11, that is your house to inspect.
Exactly. I think in the end, because we went when we went to Albania as part of the EFEHR team, I think most of the assessment of the heavily damaged building was already finalized, but they have these tablets, iPads that more or less the same tool in a more sophisticated way, more criteria, more screws to turn, etc.